welcome. And you really should be at the key signing, but thanks for coming anyway. I'm going to give a quick presentation about the state updates to Wine's Direct-to-D support, update to the OpenGL drivers as from our point of view, and new performance evaluation. I gave a similar talk last year, and this talk will, for a big part, focus on what has changed and what will change in the next year. So, what's new in our Direct-to-D code? Not too much from a user point of view. There have been plenty of bug fixes. We now have a fixed function replacement pipeline with a vertex shader, a GLSL vertex shader, which allows us to take care of some corner cases that OpenGL fixed function doesn't support. And it's one more step towards being able to use the OpenGL 3 core profile. But there are still many more things to fix for that. And we have done plenty of under-the-hood cleanups and code refactoring, in part for the command stream. I'm going to explain about more later, and for Direct-to-D 10 and 11 support. But first, let's have a look at the performance situation compared to last year. So, on the Windows side, not much has changed, which is not really a surprise. The cards I tested are not the newest one. They are 3 to 4 years old. They are still supported by the newest drivers, but there is not much maintenance. The games, however, have changed a bit. So on Windows, Half-Life 2 is faster compared to last year for whatever reason. I don't know. I cannot look into either Half-Life or Windows to find out what's changed. Xonotic is faster. I guess they improved their code over time. And the Unigine Heaven benchmark is slower, but it's also possible that I think I ran it at lower settings last year, but unfortunately I didn't write down everything, every little detail. So I don't know for sure, but it's about 30% slower compared to my Windows results I got last year. On the Linux side with Wine, I'm doing daily performance tracking. You can see from this graph that I'm updating the Wine version. This one here is an older version, about a year ago. This one here is the newest version from a week ago. Michael Laravel still has to fix the bug that it's in the wrong direction, so if he can see this at some point, consider this a request to fix that bug. So what changed? We have one time where the performance slowed down and then recovered to pretty much the original place in our GLSL code path. I don't know why that happened. I noticed it after it fixed itself, so I never bisected it. And you see the OpenGL replacement shader, which caused a performance drop at some point. It was ultimately a bug in Mesa because they did not remove redundant code we inserted, but the other drivers removed it, so we considered this something Mesa can fix. And a while later it was fixed and performance went back to the original level. And here we had another performance regression that unfortunately I didn't bisect either, so I suspect that happened because I updated that machine to GNOME 3, which introduced forcefully desktop compositing, but it's still on the to-do list either for me or a volunteer to run a bisect over Wine and Mesa to see if any of those caused the regression. So the application that has to tier was 3D 2000. I picked that one to demonstrate this because it clearly showed the GLSL pipeline replacement regression. Games that used shaders on their own did not have the regression, obviously. Here is another game. This was Unreal Tournament 2004 using the GL renderer, so no Wine-D was involved, and you can see that over the past few weeks performance has been steadily declining. So I'm pretty sure that's either updates to my desktop as well, or to Mesa. On the brighter side, the R600G driver has seen some improvements, let's say here in Fosdem 2001. Again, read this from right to left, so something that seems to go down is actually going up. And this improvement can be seen even more clearly in Unity in Heaven, which used to run at a slow 2 frames per second with the settings I'm running it at, and now it's at 80. So this has most likely been the shader optimization work done to this driver. So that's a nice job on their part. And if I switch back and forth between these slides, you see that the improvements happened at the same time. So that's clearly something that did not just improve one game. Here is the NVIDIA legacy driver, which essentially just draws a flat line, except for the part where I accidentally clocked down the CPU at some point. And then I ran a benchmark and a regression test and noticed that even the old versions didn't have that, even the old versions that used to be faster have the slow performance, and at some point I realized what is screwed up and fixed the CPU clock, and now I'm back to the old one. So to sum up the performance changes, there is not much to see in Wine, which is not necessarily a bad thing, because there's been plenty of code cleanups, and we introduced the GLSL pipeline replacement, which could have caused much worse performance regression, considering that we changed a pretty central part of the code. It's not a big surprise that the NVIDIA legacy driver is unchanged. R600G, as you could see, was substantially improved. We will see later that it's still quite a way away from Windows. And R300G was mostly unchanged. It's, after an old driver, I guess not many people, there aren't many people maintaining it. There is a patch there every now and then, but it's just sitting there. It's still working, but not much work is going on. So why give a big presentation about something that didn't actually change anything? Well, there is some work coming up from my and Henri's side, which is the multi-threaded command stream in our DirectD implementation. The basic idea is to move OpenGL calls and part of our work from out of the applications thread which calls D2D and just write into a command buffer, and have a separate thread that passes the command buffer and asynchronously executes those calls. So in many applications, if you profile them, you will find that like 40% of the time is spent in the game logic, 40% of the time is spent in the OpenGL library, and then there are mixed 20% spent for sound, input handling, and a few other minor tasks. And the basic idea is that if you split those 40% OpenGL code, move it to a separate thread, then both have their own CPU core to run, and the basic theory is that it could, in good cases, double performance. It's not really... A common misconception about this is that it's cheating because we're now using more hardware power to get better performance, but it is something that Windows has been doing since years, and last year I identified the lack of that multi-threading capability as our main shortcoming compared to native DirectD. As I said, the hope is in games that themselves are single-threaded or just do all the work. They may have more than one thread, but all the CPU-heavy work is done from one thread. That those increase, that those go up to about double the original performance. And if a game calls DirectD from more than one thread, we have a problem that currently we have to use one OpenGL context per thread and draw to the same drawers, which is legal, but OpenGL does not promise any ordering constraints between those contexts, and it's unless you flush each context after you've done the drawing, which is okay for a game that does it itself and knows it has those 5 big things it draws in each thread and then flushes once per thread. But we don't know when the game is going to switch threads and have to flush every time we do an OpenGL call. And in some situations we have to call GL finish, and everybody who knows this API knows that this is going to kill performance. And this behavior is controlled by a Wine setting. It's disabled by default because it's just terrible, and this setting is called strict draw ordering. And we usually have people filing bugs, yeah, I have to enable strict draw ordering for this game, and it kills performance. The good thing is about our command stream, since we are writing to our own ring buffer, we can do the synchronization ourselves, and we don't have to force OpenGL to do it for us. And writing to this log-free ring buffer is much cheaper than calling GL flush after every draw call or clear or texture upload. And in some games like Call of Duty Modern Warfare, I've seen 3 times the performance we had before with strict draw ordering. So the game went from 30 to 40 frames per second in pretty uneven gameplay to about 80 to 120. And it's much more fluent, well, on this hardware, at least until the hardware runs hot and the driver decides to throttle down. So I have then redone my benchmarks from last year, comparing the Windows driver to the Linux drivers and Wine. And I'll go into that, but before I do that, just some basics about the benchmark settings. So my policy is not to use any hacks, just to use the default code, the default settings for drivers and Wine, because otherwise you can say, well, but this game is twice as fast if you add this little hack, and at some point you are just messing around with hacks and not giving a fair representation of the performance a user who doesn't know about all those tweaks will see. But what I did on all systems was just ensure a sane system state. So on Mesa-based drivers I installed the S3TC library, otherwise many games don't run, or they run slowly. Whenever I could disable compositing, I disabled it, but that's mostly Windows these days. macOS has compositing on, GNOME 3 has it on, and I think one system I benchmarked with KDE where I could turn it off. And on Windows I made sure that there is no malware running, and I stopped all those nasty background processes that insist on starting up at boot time to make some huge applications start instantly because it's already running, but then slow down the entire system. Because anybody who uses Windows knows that problem. So that's the basic starting point. So let's see how fast things are nowadays. I started with a GeForce 460 GTX GPU using the binary driver on Linux. And the way that these graphs work is the blue bar is a setting at running the games at low resolution settings. Those are mostly limited by the CPU power and how fast the CPU can generate commands to send to the GPU. The red ones are with high resolution, so the performance of the execution ends of the shader is much more important in the red graphs than the blue ones. You can't compare the blue one to the red one, but just compare the blue ones to each other and the red ones to each other, and what you see on the binary driver is it's essentially the same everywhere. I used Windows as a reference point. Those are OpenGL games running on Windows compared to the OpenGL games running on Linux. And the NVIDIA driver has a multi-threaded command stream on its own, which is enabled by an environment variable. But overall, it does not change that much. It improved some games quite a bit, and it slowed down other games quite a bit. So in the end, it just cancelled out in the comparison. And here are two Windows games that have an OpenGL renderer and a Direct2D renderer compared to each other, so that you get some idea how the APIs compare. Don't read too much into that. That was just Unreal Tournament 2004 and Unigine compared D3D and OpenGL on Windows. So the essential result is the NVIDIA driver has pretty the OpenGL driver, the OpenGL part of the driver and the D3D part of the driver run pretty much at the same performance on Windows. So if we now throw in Wine and Wine's Direct2D performance, in this time the reference is Direct2D games running on Windows compared to Direct2D games running in Wine and running in Wine. And the result, if you use plain Wine without either any of those multi-threading features of the driver or Wine itself, you'll see that the performance is about 60% of what Windows achieves, and that is pretty much the exact same result I got last year. I think last year it was like 60% instead of 61, and the GPU side was slightly faster. I think it was 65, but I mostly blame that on, I think something went wrong with UT last time. So you see, when we add any of the multi-threading capabilities of the driver or Wine, then CPU limited run will has considerably increased performance on the CPU side, but on the graphics card there is not much change, which is quite expected. So if the execution time of the commands on the CPU, on the graphics card is limiting the game, feeding more commands to the GPU more efficiently isn't going to boost performance much. But since there is never a clear separation between CPU limited and GPU limited, it could be CPU limited in the first part of the frame and GPU limited later, it still goes up a slight bit. And what we have achieved with the multi-threading is that we are, instead of 60% of Windows performance, we are about at 85 in CPU limited situations, which is about where we used to be before the introduction of dual-core CPUs. And on the GPU side, the results are a bit worse than I expected, but it's mostly because Unreal Tournament 2004 ran at 20 frames per second on Linux and at 100 on Windows. And the reason for that is the game is in some way broken. In the OpenGL renderer, it calls GL finish after every frame, and in Direct2D it locks the back buffer, which means that we have to download the entire screen content to system memory and then unlocks it, and we don't know if it's modified, so we have to upload the entire thing again. The result is the same thing as a GL finish. It forces the driver to wait for all pending commands to execute, but Windows is a bit more clever about this and doesn't download and re-upload the entire buffer, because it just, I believe that it protects the memory and intercepts the exception when the game actually tries to access it and delays the download until it sees that the game actually uses the data. So on Windows it's just a GL finish, on Linux it's a GL read pixels, GL get text image, and then GL subtext image, text sub image to upload it again, which is a lot slower. Yeah. For comparison, this is, I tested an AMD Evergreen card. I think 2010 era, 2009 as well. And these are again OpenGL tests. And what you see, I tested the open source driver on Linux, and it has, as we saw in the graphs before, in this comparison it's improved as well. So last year it used to be at about 70% of the Windows driver performance, now it's at 80%. In some games there are substantial improvements, in others there are none. So that's why on the other one hand you have this graph going up pretty high, and on the other hand modest but still noticeable improvement on in this graph. But what you see on AMD cards is that their Direct-to-D implementation on Windows is a lot more efficient than their OpenGL implementation on Windows. And this difference may not look that big, but if you compare the Direct-to-D performance to the OpenGL performance and then add in Wine's additional slowness, then you get a graph that looks about like this, which is still an improvement compared to last year when we were about 30% on with Wine, and now we are plus minus around 40. And if you add in the command stream, it's even a bit higher, but compared to the NVIDIA card, the improvement is somewhat smaller. In part because I still believe the driver is mostly GPU limited, even at small resolutions, but there is in the end there is still a lot of way to go on Radeon cards. This year I did not test the binary driver on Linux, because I tried to do that and it ran every game at 5 frames per second, and I couldn't figure out what went wrong in time. But my results last year were that the binary driver was about 10 to 20% faster than the open source driver, and back then I concluded there isn't much use for it, at least on that card. There may be more use for the binary FGLRX driver on newer cards than this comparably old one, but I don't think there is much to worry about this old binary driver. And finally I have one more NVIDIA card, this time an older one. The main point why I tested this again is that this card was part of a Mac system, so I could test OS X, and the results were pretty much all over the place. The CPU limited part was pretty awfully slow, which even in just, again, OpenGL games here, no Direct-to-D involved, which more or less matched my expectations, but at least in one game, in Xonotic, macOS beat the hell out of Windows, which is why the GPU limited graph shoots up to 120%. I have to do more investigation to see where those differences come from, but don't read too much into that, but it gives you a rough idea about how OS X compares to Linux and Windows, at least on NVIDIA GPUs. But on the Linux side and Windows OpenGL versus Windows Direct-to-D, the result is the same as on the newer card. And the Direct-to-D results with Wine are pretty similar as well, about 60% with plain Wine. But one thing that was noticeable was that on this old system, the improvement from the command stream was a lot smaller than on the new one, and that's a problem I still have to figure out. And if you take the comparably bad OpenGL result from OS X and add Wine's inefficiencies, you end up with pretty terrible performance at the end. So to sum things up, the CSMT in this case is the registry setting you use to enable my code once you've checked it out from the Git repository, so hence the name. What the improvements of that are is that the main improvement is that it fixes fundamental shortcoming we used to have. And we used to be in a situation where every game was slower than on Windows. Some more, some less, but whatever you ran, it was slower. And now there are many games that are improved. Some games like Dösinger 2001 and the Unigine Direct 3D renderer are now considerably faster than on Windows. We still have other games like Unreal Tournament 2004 that are still at 20%. But it's no longer the case that Wine is necessarily always slower than Windows. But there are still some remaining problems. So the biggest one is that it's not in the Wine repository yet. There are still I still have a lot of cleanup work to do. And the synchronization between the two threads nowadays is mostly based on busy waiting. So it will just occupy 2 of your CPU cores 100%, which is okay if you have a desktop PC, you don't care about power consumption, and you have a quad core for sound and chat utilities or whatever you use. But on dual cores, it causes some problems. So I got some feedback that things like running TeamSpeak in parallel to the multi-threaded setup is resulting in stuttering sound because TeamSpeak doesn't get enough CPU time, and 30% of the CPU time of one core is just spent waiting either for commands to arrive or commands to be executed. So I tried a few attempts to use more efficient synchronization that can actually put the threads to sleep, but I didn't have any good results with that yet because it should be portable. So ideally, I'd use in32 primitives for that because it's just available in Wine. But most of them go through Wine server, and then you have a network call to Wine server, network transfer back for each lock and unlock, and performance is just crappy. And 2 kinds of operations that are not efficiently handled yet and cause lower performance than necessary are shader constant updates and resource updates. So those currently involve at least 1 extra memcopy operation. The long-term hope is to use uniform buffer objects for shader constants and use ARB buffer storage to handle buffer uploads. So one problem is that we cannot use GL map buffer range at the moment because if there's an asynchronous buffer map, after a draw call from the buffer, we map the buffer, and then the draw call cannot finish until the application unmapped the buffer, because in plain OpenShell you can't draw from a mapped buffer. So then we have to wait for the application to unmap, but if the application doesn't unmap before another buffer is mapped and the second buffer map is a synchronous one and waits for the draw call to finish, we have a deadlock. So currently I have to use a system memory buffer and then use GL buffer subdata to upload the contents, which implies an extra copy. I've already mentioned the synchronization problems. One other issue, especially about synchronizing access to busy resources, is that there are many approaches, and some games prefer this approach, others prefer another approach. And by just shifting around a few things, you can increase performance in one test by 30% and cut performance in another test in half. And there is the danger that we over-optimize some benchmarks. And again, as is seen in the performance comparison, right now the main profits are in areas where you had plenty of performance anyway. So if your game ran at 200 frames per second, now it's running at 400. If your game ran at 20 frames per second, now it's running at 25 if you're lucky. And it would be much nicer if the 20 frames became 40 and the 200 became 210, but that's not how it turned out. So that's not how it turned out so far. And of course there's the usual issue with drivers whenever you're doing something crazy and new. And the NVIDIA driver sometimes refuses to execute those GL buffer subdata calls asynchronously. Basically it can do that, but in some cases it just says no, I'm going to wait until the GPU is idle and then I'll upload your data. And the result is that the performance with the command stream is worse than it was before. We would also like to call GL map buffer range in the thread, in the games thread that locks the buffer instead of placing a command in our command buffer and waiting for it to return. I have a mechanism to bypass already scheduled commands, so I don't always flush the command buffer, but even the round trip on the priority queue is too slow for some games. And again, here is the hope that buffer storage helps and I don't even have to call map buffer range, or at least I can call it and still draw. But drivers don't like it if we call them for multiple threads. NVIDIA crashes, I've had report of Mesa crashes, and if you do that on FGLRX, your system just dies. It works for maybe 5 minutes and then it's completely frozen. You can't even SSH into it anymore. And the NVIDIA can be fixed by using a mutex around the GL cores. I believe in theory we should not need that because we use different contexts for each thread. There's no other way than use one context per thread. So using those two contexts in parallel without locks should be okay, but if we have to add locks to map our buffers in the main thread rather than the worker thread, then a lot of performance of not calling into the worker thread, a lot of gains of that get lost again. So still plenty of things to work out. And one question which users asked me a number of times via email is how our multi-threaded command stream compares to NVIDIA's GL threaded optimization. And the answer is that they're essentially the same, but depending on what the application does, one is faster than the other. So our command stream intercepts commands pretty much at the earliest level in the D3D call, and NVIDIA's command stream intercepts them after Wine is done generating GL calls. So depending on if the GPU driver needs more time than the game logic, then NVIDIA's optimization is faster because you have the Wine D3D part on the game logic side. If the game logic needs more time than the GPU driver, then ours is faster because you have the Wine D3D time on the GPU driver side. So depending on what the game needs, one is faster than the other. Our code works on all systems and drivers. The NVIDIA thread optimizations just work on NVIDIA, and NVIDIA's optimizations don't help us with multi-threaded applications because we still have to call GL flush, and it's still horrible from a performance point of view. And I've had some arguments with NVIDIA engineers about GL map buffer range. Essentially, if you call that function with their threaded optimizations, it forces a wait for the thread, and your performance is terrible. For the benchmarks, I've violated my no hacks policy at that point and used a patch which replaced GL map buffer range with our own buffer copy and then GL buffer subdata. But without that hack, the NVIDIA threaded optimizations wouldn't do any good with our D3D code. So that's pretty much the comparison between two similar solutions. One final bit of benchmarking I did was that I compared, now that Half-Life 2 and other Source Engine games have a native Linux port, I compared the Windows performance to the Linux port and Wine. And my result was that Windows still has the advantage. But if you look at those frame rates, 600 frames per second, 450 frames per second, it's not too. It's a somewhat bad benchmark for this game, for this system, because it's running way too fast anyway. But on the other hand, even though benchmarks sometimes seem, if they run too fast, they seem bad, there's still a. They still mostly scale like the older ones, so it's not a completely useless benchmark, but it was just easy to run. So with 2 hacks in Wine, we are pretty much as fast as the native Linux board. With the command stream tree as it is, it's still it's noticeably slower, but those are that's mostly the NVIDIA's buffer update slowness that causes that. And one final topic I'd like to bring up, if I have any Mesa developers here, is the topic of draw overhead and how many draw calls per second the driver can do. And I have a pretty simple benchmark that essentially does one thing that every OpenGL tutorial tells you not to do, and it draws 1,000 cubes with 6,000, actually 12,000. I think it's 12,000. No, it's 6,000 draw calls. So 6 draw calls per cube, 1 per phase. And I compared in this case it's the Radeon card. I forgot it in the slide. I compared the performance of the test application on Windows with Direct3D, the OpenGL driver on Windows, and you can see that at least on Windows, OpenGL has a significantly lower draw overhead than Direct3D, which is mostly because Direct3D does some checks to babysit newbie developers, so Direct3D catches a few stupid things you can do if you don't know what you're doing that OpenGL does not catch. And we have the same tests as well, because otherwise some games don't work or are slow. But those add some overhead for well-written applications, or at least what you could achieve if you need many fast draw calls. The R600G driver is a bit slower than the Windows. The R600G it's considerably slower than the Windows GL driver. It's even slower than the D3D driver. And if you start off with a higher overhead to begin with, and then advanced overhead on top of it, you end up with this. And we have to improve Wine, and this is not something. Don't read too much into that, but it's something for driver developers to just keep in mind when they add extra things to their GL draw arrays and draw elements functions. Over the past few years, I improved this draw overhead benchmark in Wine to essentially achieve double the number of draw calls, and that improved real games by about 5 to 10%. So this draw overhead tester is about as good a benchmark as GLX gears, but still there is some value in keeping even a GLX gear score in mind. So that's mostly it. The steps for the next year would be, so my main goal is to merge the command stream into upstream Wine, fix and improve streaming data to the shader constants and resource updates. We also have to get serious about Direct3D 10 and 11. It's mostly on rework right now. And with the CPU side improvements of the command stream now, we have more worries with GPU side performance, especially on the AMD GPUs. So there are new areas we have to investigate that we didn't really care about until now, because we were always CPU limited. And in some games like Guild Wars 2, there are now performance issues outside the Direct2D code. So it used to be blocked by Direct2D with strict draw ordering, but when you run it with the command stream, it's a slightly bit faster. Actually, I think it still has double performance, but it's now blocked by lots of Wine server calls that drive Wine server CPU time to 70% of one core. And there are still many game-specific bugs we have to track down. Finally, the slides will be on then at some point, so if anybody wants to verify my test results, those links contain the raw data. It's just results at an openbenchmarking.org. It's a bit unreadable, but with some trial and error, it should be possible to reproduce the tests I did and hopefully come to the same conclusion. If the results are different, then I screwed up somewhere. So, thank you for your attention so far. If there are any questions, now is the perfect time to ask them. Yeah.
What do you think of a direct 3D implementation based on Gallium 3D, which would provide more native direct 3D on Windows?
I'll just repeat the question here for the microphone in the movie. So the question was about a Gallium 3D based direct 3D implementation, and if that could provide better performance by reducing overhead. Did I repeat it correctly mostly? Yeah. So my main opinion about that is that right now I don't think there is enough evidence to suggest that it's necessary. So I know that there's an implementation out there and it improves some games quite a bit, but the interesting question is if it improves the games by bypassing performance bugs in Mesa's OpenGL implementation or Wine's D3D implementation, and if those bugs are really unfixable, if those bugs could be fixed in other ways. So ideally we'd improve our OpenGL based code path that improves things on every system, and Mesa improves its OpenGL implementation and by that way improves performance in all games. So in the end I think that is right now the better long-term approach. I would be more open to a command stream, to a Gallium 3D based approach if it can really be shown that good performance can't be achieved otherwise. And I believe essentially the results on the NVIDIA binary driver. So where is it? Oops, too fast. We are beating Windows in some games on the NVIDIA binary driver now. So I think this shows that OpenGL is a useful API to base Direct3D on, and that it can be done. So once Mesa executes games pretty much the same speed as the OpenGL backends, or some games at the same speed Windows executes the D3D backends, and it's still slow on Wine, then that would be another sign that we have to cut down overhead. And I also had a quick look at the implementation that's out there. And the main problem I have with that is that there are a few, the way the interface between Mesa and Wine is designed is that it's a fairly simple interface. It just exports an iDirect3D9 interface from Mesa to Wine, and it makes most games happy, but it has some... Direct3D is more linked to the Win32 API than this interface choice supports. So window overrides in the swap chain won't work. Calling getDC on surfaces won't work. So at least the code that's out there needs a lot of restructuring to be given, so we could start thinking about merging that. The way it's currently now, it's clearly a non-starter. Yes?
They had all with the new code driver or the Intel driver?
I tested the Intel driver last year, And I was hoping to test. I have an Intel card in this MacBook to get everything in video card, but unfortunately I couldn't get it to work on Windows because the firmware just removes it from the PCI config space. So I have to install Windows 7 with eFile rather than the BIOS. It's supposedly possible, but I wasn't feeling like reinstalling Windows yet another time, so the next time I reinstall Windows I'll look into that. The results last year from the Intel driver, which I ran on a GMA 965, pretty old card, were that performance is pretty much the same as on Windows and even exceeds Windows, but at least in OpenGL games. But the driver crashed pretty much every time with a kernel panic when I tried to execute a D3D game. And I thought that rerunning the tests on that old hardware, which has the 965 hardware itself is known to be pretty terrible. Nobody uses that for gaming, so I thought retesting that hardware is a futile thing. And Nouveau, I didn't get around to test that this year either. So I started the benchmarks two weeks ago, which was again too short a notice, but maybe next year I can do it 4 weeks in advance.
Feel for the general quality of the drivers?
The Intel driver seems okay, and when I tested the Intel card on OS X, I was surprised by its performance. The Intel driver on OS X is terrible, but I don't think we have some bug reports every now and then about the Intel cards, but I don't think there is anything terrible. Henri, do you know about any terrible Intel driver bugs?
Well, supposedly some performance in i9.
Is what? Oh, the bug in the i19.5 driver. Well, that's once old, but so we don't have any terrible bugs on the known bugs on the Intel driver, which could mean that it's working. It could also mean that people just gave up. You never know. Any other questions?
Yes. With the command stream, you have improved performance a lot, but it was already on Windows, this sort of optimization. Do you think there is something more on Windows that could be added to Wine and that you don't have yet?
Well, the next step after we have the command stream working properly would be to reduce our draw overhead. The question was if there's anything else from Windows we could add to Wine to improve things. Did I understand it correctly? From the D3D part, nothing fundamental. Well, of course, RF3D 10 and 11. From parts outside of Direct2D, I don't know yet. I think we'll have to improve some of our Wine server-based synchronization things at some point, because now multi-threaded games, which used to be terrible because of the strict draw ordering setting, are now a bit faster but still terrible because they are blocked by Wine server. So that's something where we will have to look for improvements in the future. But otherwise, from a D3D point of view, there is nothing fundamental missing after the command stream is there. Yes?
Speaking about drivers, what about Wine under the Wayland and how it could be and what will be the difference in future?
So the question was about Wine under Wayland. I think it's mostly up to Alexandra. But my knowledge about this is now that we have a proper interface between GDI user and the driver backends, adding a Wayland driver is a lot easier than it was a few years ago. But I think there are some design issues in Wayland, like no global window positioning, and the by design inability to inject events to other windows. That will make supporting some applications difficult because Windows applications depend on that. Those are conscious design decisions in Wayland, so there may be some applications that will only work in a virtual desktop and things like that. Just because Wayland is by design incompatible with some Win32 things. Yes?
Just another question related to the Gallium thing. Would it be possible to leverage the work you've done on the command stream to, you almost directly level there, to also use that for the gallium or even for other backends like, Fosdem, but also in future maybe mantle?
So the question was if my command stream work could be used to help other backends of Mesa. You can't reuse the code. The code is in Wine 3D, it's written specifically for that. But I believe Mesa is working on its own solution for that.
But I do mean for wine, for instance. Imagine if you merged the gallium stuff into...
If we merge the gallium stuff, it would bypass the command stream completely. It's just that it bypasses Wine 3D entirely, so it would bypass that as well. Any more questions? So that's it.
Thank you, Stefan.